Here is the second part for the lecture today, and just a quick reminder for the right-hand rules to find the direction of magnetic field based in the current through the wires. And we mentioned about the thumbs point to the direction of the wire, the direction of the current in the wire, and the curl fingers point to the direction of magnetic field. Today we're going to continue, or the second part, we're going to continue to cover more topic regarding for the magnetic field. I will start with the more extension. So not just the one wire get the directions, but the shape, if you have different shape of the current, and we're gonna start with the circle and the circle directions, what the magnetic field directions if I have a circle wire and the current rule. And to imagine this one, imagine we have one single wires as we covered before, and we just turn that wire and we made a loop. So, and just to imaginations, we try to just as the plane cross that part, and you see the current comes from the top side and comes into the inside. And we know the direction when it goes out as the arrow, we represent it as the dot. That means the current comes out or perpendicular to the page. And when it comes in the low side here across the arrow, which means the current comes inside that paper. Okay, it's that general representation. Now the question is how I can find the magnetic field directions based in that case, based in the loop. If, for example, if I have this specific or particular point and you ask to find what the direction of magnetic field in this particular point. Okay, that's what the question for that we're gonna start with. And to solve this problem here, let's just make it generalized. Now we have the magnetic field, and we have right now with the circular wires, and we have in the top it's point out, and in the down it's point in. Let's start from the point out in the top one, where is the direction of the current is comes out to you, and your thumb it has this direction comes to you, and your curl fingers point to the direction of magnetic field, which if you look at this one, it is comes out in that direction, comes this one. So inside the loop will be point from the right to left, and inside the loop comes to the left to right. And the same concept we can dealing with the second part, where is the have the current comes inside this one here. Use the right side or right hand rules. We find the magnetic field directions out of the loop. It's point from the right to left, inside the loop from the left to right. So as a generalizations, here is the loop. All the current, all the magnetic field inside the loop, they pointed out, and all the magnetic field directions out of the loop pointed in. Okay, so back to our questions here, based in this representations here, we find the current direction or the magnetic field direction, and that this point here will be to the left. Now to write down the formula, to find the formula to find the magnetic field, in our case here, when we have just the radius of the circle, or the circle or the wire circular pointed as the R, here the magnetic field of the loop, it has a formula mu times I divided by 2R, with the R the radius of the circle. And to make it, so this is the formula, it's work to find the magnetic field at the center of the loop. Now, if I have multiple loops, that's the formula would be kind of the complicated. But here we're gonna just write it down the formula as the simple way, so you don't have to deal with that complexity of the find that one. And here's the formula. It is stated that the P inside the coils is the same formula. It is to find the center of the loop, and but type is N, where is the N number of turns, where I have the many loops that are put aside to each other. So that's the formula to find that if I have n number of chair in the loop. Let's take an example to apply that concept, how we have here what the magnetic field, size, and directions at the center of this single coil. The single coil means n equal 1. So the formula that I will use is mu 0 I times 2r. There is no 2 pi. Okay. So let's find the direction first. So I have the current here. So I need to use my right hand, where is my thumbs point up to the direction of the current, and we need to find out what the direction of the magnetic field at the end or at this point here inside the loop. Okay, take a moment to think about it, what the direction of magnetic field. Okay, let's see our right hand rules. Here is our thumbs point to the current, and here is in that case the magnetic field direction inside the loop. They will be pointed out, included the point of the center. So here's gonna be pointed out the page. That's the direction. Now we go to find the magnitude. My magnitude will be P of the loop up. Sorry about that. So here is the P loop. I have mu 0 times I divided by 2r, whereas I have all the value. Mu, it's 1.26 power to the minus 6. Here is as a unit. Tesla times meter divided by area times the current in that case here is 3 amps. 3 amps divided by 2 times R, where is the R 2 centimeters. So here is the 0.02 meters. As a unit, current cancel current, meter cancel meters. I end up with the Tesla 9.5 power to the minus 5 Tesla. So here is the P of our loop. Okay. And for the directions will be out of the page. Okay, so that's the regarding for find the magnetic field for the loop one. If we are given a number of the turns, we just type or multiply this number with the number of the turn. Okay. And that lead us for the new concept or the application solenoid. And the solenoid here is just based in the number of the turns they are connected together. I have a wire, and that the wire I create the n numbers or the n loops. So n loop from that case, and they are adjacent to each other. And the magnetic field in that situation is here. Here is the for solenoid is the mu times n, where is the n number of turns, how many turns you have to represent that solenoid, times I divided by L, where is the L, the length of the wires. The interesting part here is that the magnetic field of the solenoid, it doesn't dependent on the number of the loops. It just non-dependent about, not non-dependent about the radius of the loops. Here's the number of the loop, but it doesn't matter is small or big, is totally independent with the radius, with something very interesting one. And usually for that case here, we're gonna find use the right hand rule to find the direction of magnetic field, where is the our thumb will be pointed to the direction of the current, and the curl finger pointed to the direction of magnetic field in both cases. And here is the drawing cross section. If the solenoid, how it comes to, here is the top one will be dot, and the lower side will be cross pointed toward the page, and this one's the out of the page. And you look at the magnetic field out of the solenoid will be pointed from the right to left, and inside the solenoid pointed to the left to right, and that's the direction of magnetic field. And the interesting part here, the magnetic field inside the solenoid, it's gonna be the same for all the point. So exactly as the magnetic, as the capacitors. So all the electric field or electric field line in the capacitors that has the same value in all set or on all places between the plates. And similarly for the solenoid, all the point inside the solenoid has the same magnitude of magnetic field. That's the interesting part with that case. And now let's see how to apply this concept or practice an example. And here we have the coupled wires, and we wrap this around the iron nail, and the resulting the coil wire consisted. Here is the number of turn. We have 240 turn of the wires, and the cover 1.8 centimeter, which means that's the length that we are focused about it. And the iron nail increased the strength of the magnetic field nail by factor 100. So this is the 100 times solenoid the magnetic field. So the current is energize that wire using the battery or something, and we give us the current 0.6 amps. And they ask to find the magnitude. What is the magnetic field strength inside the solenoid, inside the nail, which that's basically solenoid. So the formula that we're gonna use, mu n times I divided by L. So here, if I wanna write down my formula, here is the P of the solenoid. It would be mu 0 times N times I divided by L. Divided by L. Let's write down our numerical value in that case. Here is the mu, 1.26. Sorry, 1.26 power to the minus 6. Here is the Tesla meter divided by amps. Divide by N. In that case, how many turns? I have 240 turns. Times I will be 0.6. Divided by L. What I have here is for the L, 1.8 will be 0.018 meters. Now, since we have, let's see, since we have the vector 100, so that means my P nail in that case, P nail or the magnetic field inside the nail will be 100 times P solenoid, what we calculated here. So I have just this number here times 100, I end up 1.0 Tesla. Again, this very remarkable value. We mentioned about the Tesla, it's very small value. So that's one, using that wires and with the nail, we generate a huge magnetic field as a magnitude. Okay. So this is the practice example regarding to find the magnetic field for the solenoid in example. And we have the N-turn loop. Okay, I stop with that lecture for today, and see you next video, guys. Thank you.